Hello everyone and welcome back. Now we are going to look at the continuous time versions of the unit step and unit impulse sequences which we have defined in the previous clip. So just like before, the symbols are the same for the unit impulse signal. The symbol which we are going to use is the delta, but since we are now talking about the continuous time version, so we are going to represent it with delta t. Similarly, the unit step signal to represent it, we use the notation the U. So we are going to use the same notation U. And again, now since we are talking about the continuous time version, so we are going to represent it like U of t. Now, there are some differences when it comes to the discrete time versions and the continuous time versions of these signals. So let me just write down the definition of the continuous time unit step signal first. So the continuous time unit step signal can be mathematically defined as U of t is basically equal to 1 for t greater than 0, and the value is 0 for t less than 0. So if you're wondering what's the difference between the discrete time version and the continuous time version, so let me very quickly write over here the discrete time version over here. So the discrete time version was u of n. It seems same, but there is a one difference over here for n greater than equal to 0 and 0 for n less than 0. So now I believe you can see where the difference is. So the difference is actually that continuous time unit step signal is not defined at t is equal to 0. So continuous time unit step is not defined. The signal is actually not defined at t is equal to 0. So it's essentially a discontinuous signal. It's not defined at t is equal to 0. And one might wonder why it's not defined at a t is equal to 0, because the continuous time unit step signal is used to mimic the switch operation. So in the natural switch operation, you're going to have two states, on state and off state, and there is going to be some delay when basically you turn on the switch. So there is going to be some time instant where you will not have any state. So that's the reason that unit continuous time unit step signal is basically not defined at t is equal to 0. Okay, so let's see how this implicates the things for the impulse signal. We are going to look at it in a more, but let's just first quickly plot it. So the plot is again same. It's very simple and same. So you simply plot the axis first, right over here, u of t, mention the origin, and then you basically, for t greater than 0, which is basically this region, you draw a straight line. For t less than 0, which is this region, you draw a line on the 0 axis. So the amplitude is 1. So at t is equal to 0, the signal is not defined, but usually in the Oppenheim book, when we are sketching the unit step signal, we tend to connect these 2 points. That is also fine. So this is how the unit step signal you are going to plot it. So it's understood that a t is equal to 0 signal can't have a value of 0 and 1, so it means it's discontinuous at this time. So this is the visual representation of the unit step signal. So just like before, we are now going to look at the how we can represent the unit impulse signal in form of the unit step signals, or the unit step signal in form of the unit impulse signal. So like before, just like before, we have seen this expression. I'm going to write that expression again over here now. For the discrete time case, we saw this particular expression, which was u of n was basically defined as delta. Let me quickly, yeah, u of n was basically defined as like this, delta m, where m was from minus infinity to n. So this was the version which we have already seen, which we have already proved for the discrete time scenario. So using the same uh, formula again, we can write this expression for the continuous time domain now. So for the continuous time domain, the expression is now going to be u of t, and then instead of the summation, you are going to have an integral. So it's again minus infinity to t. and then you are going to have some dummy variable inside. So in this case, the dummy variable we are going to say is tau. So this is the expression of unit step signal represented in terms of the continuous time unit impulse signals. Okay, so another expression which we can write as well, which we have already studied for the unit step for the discrete time versions, was this one, which was u of n can be represented as delta n minus k, where the limit basically goes from k goes from 0 to infinity. So that was a second relation which we have already studied in the previous clip. So if you want to use the same expression again, if you want to use this particular formula for writing, you can write it again. So now in this case, the formula is going to be u of t, and then summation is going to be replaced again with the integral. So 0 to infinity, and then we are going to use delta t minus, again you're going to have some variable, so let's take a variable sigma d of sigma. So here now you have actually two relations written for the continuous time domain now. So the two relations are written now for the continuous. So these were we have already studied these one the discrete time domain formulas, these ones, and now these ones are the continuous time domain formulas. Okay, so let's now see how we can define the continuous time unit impulse signal, because we will see in a moment that we will need to derive its relation. It's not straightforward. Okay, so by taking this particular expression which we have already written over here, which is that unit step signal u of t is basically equal to minus infinity to t and sigma tau t tau. So we are going to use this expression to write or derive the expression for the continuous time scenario. Okay. So now if you want to find out if you want to write the expression for this particular signal, which is the impulse signal, we can take the derivative on both sides, and then continuous time unit impulse signal is basically equal to the derivative of continuous time unit step signal. So that is one expression which we can use to define the continuous time unit impulse signal. But the question over here is now that we need to compute the derivative of a unit step signal. And unit step signal is already drawn over here, and we have mentioned this thing that it's not defined at t is equal to 0. So this makes things a bit tricky, because you cannot compute a derivative of a discontinuous function. So at t is equal to 0, my signal is not defined, so it's not possible for me to compute this derivative. So what we are going to do is we are going to make an approximation of this particular unit step signal, which is going to be a continuous, it's not going to be a discontinuous, and then we are going to try to find out the derivative and see how we can reach this approximation. So the signal which I'm going to take for the moment right now, so let's draw that. So I'm going to call it u delta t. Okay, so this particular signal which I'm going to take right now is not going to be a discontinuous. So at t less than 0, the signal is going to have 0 value, but then there is going to be some slope like this, and then it's going to have a value of 1. Okay, so what you can see now that signal has for t less than 0, the signal value is 0, which is fine, and then we are saying that it rises to a value 1, and that particular time which it takes to rise to the value 1, we are going to call this delta. So this particular point is delta, this is 0. Okay, and then it attains a value of the 1. So essentially what we have done is we have tried to actually create a version of this unit step signal which is a discontinuous at t is equal to 0, and drawn this thing which is no longer a discontinuous signal. Now it's a continuous signal, so we can take a derivative of this one. So let's try to take the derivative of this one and see what the result is. So now if I take the derivative of this thing, So d by dt u of delta t. So that is what I need to do. And then the derivative of unit step is going to give me the impulse function. But I'm going to write delta over here as well to give me an indication that this is an impulse function which is derived from u delta t. Okay. So now we need to take the derivative of this thing. So derivative is basically slope of a signal. All right. So what we can see is that for t less than 0, the slope of the signal is actually 0. Similarly, for t greater than delta, which is the region, uh, this region, after this region, which is t greater than delta, we have a straight line. So the slope is again 0. Similarly, for t less than 0, which is basically this region now, this region, again we have a straight line, so the slope is 0. So the only region where we are going to compute the slope is from 0 to delta. All right. So let's write the expression first. So what d by dt is essentially a slope. So the slope is going to be defined in only from t0 to delta, and we are going to write the slope over here. And for all the remaining values, for all the rest of the values, I'm going to write otherwise. For all the remaining values, the slope is actually 0. Okay. So let's calculate the slope now. So for calculating the slope, we already know the formula is, to calculate the slope is m y2 minus y1 x2 minus x1. So we have 2 points. We have this point where the coordinates are 0, 0, and then we have this particular point where the coordinates are delta and 1. All right. So if we substitute these values now inside these expressions, so what we are going to see is that this is 1 minus 0, and the x-axis is basically delta minus 0. So the slope comes out to be 1 upon delta, right? So the two y values were 0 and 1. So these are the two y values, and the two x values were 0 and delta. So we have substituted the values and found the slope to be 1 upon delta. So let's write the slope now. So the slope is 1 upon delta. Okay. So let's try to plot this thing now. This impulse delta t, which is basically this particular thing which we have defined over here now. Okay. So we plot the axis first. All right, so like this. Okay, so let me just quickly erase this thing. All right, so this is 0, and then let's take this point to be as a delta, right? So the signal now is that between t0 and delta, the signal value is 1 upon delta, which is a constant value, which means I have a straight value like this, and the value, the amplitude, is 1 upon delta. All right, so this is not a function of a time, so it's a constant. Okay, and for all the remaining values of the t, the signal has a 0 value. So I'm going to draw a signal like this. Okay, so for t less than 0, it's 0. For t greater than delta, it's again 0. But between 0 and delta, the value of the signal, the amplitude, is basically 1 upon delta. Okay, so now let's get back to the approximation which we actually assumed in the beginning. So our approximation was that from the u of t, we actually plotted the u delta t and then did all this derivation. Now u of delta t is going to approach to u of t, which means that this particular signal is going to become u of t, this particular signal, if delta approaches to 0. Okay, so I hope it makes sense. So if you move delta towards 0 point, this point is going to come towards this axis, the y-axis, and then you're going to basically approximate this particular signal, which is the continuous time unit step signal. Okay, So if delta approaches to 0, what is going to happen to 1 upon delta? If delta approaches to 0, 1 upon delta is going to approach to the infinity. All right. So now we are going to define the continuous time unit impulse signal. Okay, another important bit which we need to mention over here is that the area of this signal is actually 1. So its base is delta, its height is 1 upon delta. So you multiply base by height, so it's going to be 1. Okay, even if we reduce the delta as delta approaches to 0, if we reduce the delta, what is going to happen? If we take this as a new delta now, so as we reduce the delta, 1 upon delta is going to get higher and higher. So maybe if we reduce the delta, next signal which we are going to get is going to be something like this. Okay, so if we take this as new delta and call it delta dash, then my impulse is going to be of 1 upon delta dash height. And again, interestingly, if I take the area again now, again the area is going to be equal to 1. So irrespective of what the delta value is, the area of this impulse is always going to be equal to 1, and that is the area. Okay, so now let's let's draw the continuous time impulse signal. So what we have seen is that when u of delta t approaches to u of t, that's when this signal which we have plotted over here, this is the signal which we have plotted, is essentially approaches to this thing. Okay, so for this to happen, the delta should approach to 0 and 1 upon delta is going to reach to the infinity. So let's try to plot this thing now. Okay, so t and delta t, right? So we are now drawing this thing from this one, and this is going to be drawn when delta approaches to 0 and 1 upon delta approaches to the infinity. So how we are going to represent the continuous time unit impulse signal is by this way. So we are going to draw a line at 0 with an arrowhead mentioned like this and 1 written over here. So what does this mean now? This is the representation of continuous time unit impulse signal. Its width is approaching to 0. Its width approaches to 0. Its amplitude, which is the amplitude or height, approaches to infinity. But its area is going to be equal to 1. So this arrow shows that the height of the continuous time unit impulse signal approaches to the infinity. And when we draw it like this shows that the width approaches to the 0. But the overall area of the continuous time unit impulse signal is going to be 1 always. So this is the representation of a continuous time unit impulse signal. Well, please remember that basically this signal is not realizable in the practical sense, because in the practical sense we are always going to have something like this which is going to have some width. It's going to be like a pulse, but it's a mathematical representation which we are going to use frequently in the course of the signal and system. Okay, so now what you need to remember is whenever you're plotting the impulses, I would highly urge you to be very careful whether you are trying to plot a continuous time impulse or a discrete time impulse, because the way you draw it is going to dictate whether it's correct or not. So just finally, I have drawn the continuous time impulse over here. So this is a continuous time unit impulse, right? So the continuous time unit impulse is always going to be drawn with an arrow, and the discrete time unit impulse, if you are plotting that one, although we have plotted it before in the previous lecture, but just to revise that, n delta n 0. So it's always going to be drawn like this with a sample value. Okay. So this is the discrete time unit impulse. So what's the difference? Over here, this one is the amplitude of the signal. Over here, this one is basically the area of my pulse. So actual signal is this one. Okay. So always draw the continuous time unit impulse with an arrowhead, and the discrete time unit impulse, you are going to simply plot the sample. So this is one of the most commonly occurring mistake which we find in the quizzes and in the papers, that while drawing the impulses, they are going to draw either this one when asked to draw the discrete time, or draw this one when they are intend to draw the continuous time. So please be careful in this sketching whenever it comes in your problems. So now we are going to look at a few properties of the impulses and unit step signals, and also we are going to look at how we can represent different signals in form of the unit impulse and unit step signals. So we will come to this topic in the next video now. Thank you.